And now we are going to listen to Aurelien Crida, who is going to talk about planet-disk interactions. So please.
Thank you very much. Hello everybody, and welcome aboard this PP6 talk to planet-disk interactions and the early evolution of planetary systems. Our captain today is Clément Baruto, and I am Aurelien Crida, speaking on behalf of all the crew, listed here in alphabetic order: Bertram Beach, Jérôme Guillet, Wilhelm Klei, Frédéric Masset, Samian Parde-Cooper, Richard Nelson, and John Papaloizou. Our talking time today will be approximately 35 minutes. This is a non-smoking talk. There are 2 emergency exits in front of the room and 2 in the middle of the room. But please remain seated, even in case of unexpected MRI turbulence. Now let's take off, starting from ground level statements. Planets form in protoplanetary disks. In particular, the giant planets are mostly made of gas, hydrogen and helium, and so they must have acquired their final mass while they were still embedded in the protoplanetary disk. So from their core and the constituents of their core, if they form by core accretion, to the giant planets, there must be planet-disk interactions for various masses. And just to make it even more clear, I show here a few evidences of planet-disk interactions that will be mentioned in this talk. Mainly the hot Jupiters probably track inwards migration. There are also resonance systems that we think are due to convergent migration. And there are also compact, coplanar, low-mass, multi-planet systems that probably track migration and formation of planets inside the disk. To start with, what are these planet-disk interactions? If you put a planet here on a fixed circular orbit around the star at the center of this simulation, you see that the planet, by its gravity, perturbs the fluid and launches a spiral wave. This spiral wave is a pressure-supported wave that we call the wake, and it co-rotates with the planet with the same angular velocity. This is just what you see when you put a planet into a disk in a numerical simulation. It's inevitable. You get this spiral wave. The light color in white corresponds to an over-density. And so what is the effect of the disk on the planet? Well, this over-density means a mass, and a mass attracts another mass, that's gravity. So there is a force from the disk on the planet. You can't avoid that. And this force has a momentum, so it translates into a torque that we note gamma. And the torque gamma is the derivative with time of the orbital angular momentum of the planet, Jp, which is proportional to the planet mass and square root of J, mass of the star, and radius of the orbit of the planet. So a torque means a derivative with time of the orbital radius. You have drp over dt is equal to, is proportional to gamma divided by the mass of the planet. So in what follows, I will focus on gamma, and what we study when we study migration is the value of this gamma, its sign, its amplitude, because gamma is directly linked to migration because it's just the derivative of the orbital angular momentum. So a planet in a disk feels a force, and therefore it changes its orbital radius. This is planetary migration. Now, what is the effect of the planet on the disk? Well, the planet as well exerts a force on a disk. It exerts a torque on the disk. And so I will tell you under which condition a gap opens or a cavity opens, what is the feedback on this on the migration, and what is the link between these structures and the observations. So this is the outline of my talk. I will start by telling you about a single planet of various mass ranges. Then we will see what happens when you take a pair of planets and things are slightly different. And we will also review comparison with the observations that are made. So let's start with small mass planets, which are in what is called a type 1 migration. In that case, the torque, gamma, scales with this gamma 0, which is proportional to the planet-to-star mass ratio Q to the power 2, and the density of the gas, sigma, capital sigma, the surface density of the gas, and inversely proportional to the square of the aspect ratio of the disk, h, which measures the pressure. So this is an old, well-known result, and to give you an idea of what this gamma 0 means, actually, if you take the surface density of the minimum mass solar nebula at 1 AU, then the migration time, the typical migration time in years, is roughly equal to 1 over Q, the planet-to-star mass ratio. So for an Earth mass planet, it means a migration time of the order of 300,000 years. That's fast. And for a Neptune mass planet, it means a migration time of the order of 20,000 years. It's even faster. As the torque is proportional to the mass of the planet squared, the migration time is inversely proportional to the mass of the planet. So we need to understand how this torque is, and the torque due to the wave in a 2D adiabatic disk reads like that. We call this torque due to the wave gamma L, and it's equal to gamma 0 multiplied by minus 2.5 minus 1.7 beta t plus 0.1 alpha sigma, where this small gamma that you see here is the adiabatic index, and alpha sigma is the negative of the power index of the density profile, and beta t is the negative of the power index of the temperature profile. This is a result from Pardo-Cooper et al. 2010, but there has been other estimates consistent with this one before. And in general, the slope of the density profile is between 1/2 and 3/2, according to observations. And the slope of the temperature is about of the order of 1 over r, so beta t is of the order of 1. And if you put beta t equal 1 and alpha sigma equal 1, you get a negative torque and a very fast inwards migration. So this is more or less where we were at PP5. But it's not the end of the story. Let me show you first how this fast migration occurs. Here the planet is free to evolve. We are in the co-rotating frame with the planet, so we don't see the planet turn. We rotate the camera on top of the disk, if you like. And you see that the orbit of the planet shrinks. The planet approaches its central star. And in this particular case, where the density was relatively high, in about 200 orbits, the migration is already very significant. So I told you this is not the end of the story. Indeed, around the planet, close to the orbit of the planet, the gas, if we trace the streamlines of the velocity field, here is what they look like. You see the streamlines of the velocity field. Actually, they look like a horseshoe. So the gas here, on average, co-rotates with the planet. And this region that I highlight here in yellow, between the inner disk in blue and the outer disk in red, is called the horseshoe region, and it exerts on the planet a co-rotation torque. The wave torque comes from the inner and the outer disk. The co-rotation torque comes from this region. And it has been really studied in detail in the last 7 years or so. It reads like this. Again, it's in units of gamma 0, and the first term in this sum is the barotropic part, which is relatively easy to understand because it is like when you swim. It's like crawling. You see that the planet here sends to the sends outwards the material that is coming inside its orbit, and on the other side, the planet sends inward the material that is coming outside of its orbit. That's the geometry of the horseshoe region. So it's really like when you are crawling, right? You have one arm pushing material backward and one arm pushing material forward. And if you swim at the surface of the water, your arm pushes water behind and air in front of you. As water is heavier than air, you move forward. But if you try this move deep in the water or here in the air, you don't move. So that's why this part depends on the density gradient here, obviously. And there is a second term here, which is due to the advection of the entropy. That's why this psi here, equal to beta t minus gamma minus 1 alpha sigma, is actually the logarithmic derivative of the entropy. And this one is due to the fact that the material from the inner disk is actually hotter than the material from the outer disk. That's why it's blue here. We know that blue stars are hotter than red stars, okay? So when it's advected here, it finds itself in a cold region, and as it is hot, it expands. And this makes a region that is less dense here behind the planet. And symmetrically, the cold material advected by the planet here contracts because it's in a hotter environment. So we have here an excess of mass in front of the planet. So this leads to a positive force on the planet in the direction of its motion. So a positive torque. You see this big, almost +8 psi here. And as psi is generally positive and alpha sigma is generally smaller than 3/2, this co-rotation torque is in general positive, and it can even overcome the wave torque gamma L, which would lead to outward migration. Actually, the total torque, if you simplify it and assume that gamma is 1.4, would read like that, so minus 0.64, minus 2.3 alpha sigma, plus 2.8 beta t. But this is not yet the end of the story. Achtung. This corresponds to the co-rotation torque on circular orbits and unsaturated. This expression here is only true for circular orbits, and the co-rotation torque gamma c tends to 0 when the eccentricity of a planet increases. Fortunately, the disk damps the eccentricity of the planet, but still this is to be kept in mind. And also, the co-rotation torque is prone to saturation. Saturation is a complicated phenomenon, but actually very easy to understand. This horseshoe region, it's a closed region. So it has only a limited amount of angular momentum to exchange with the planet. And if you do not refresh this angular momentum content through viscous exchanges with the outer world, well, at some point, the co-rotation torque has to dump to 0 as well with time through damped oscillations. Here, you see the total torque felt by a planet in disks with various viscosities characterized by the alpha parameter. And you see that for small alphas, the co-rotation torque saturates, and the total torque is about equal to the wave torque. But when alpha increases, the total torque now reaches the co-rotation unsaturated circular torque plus the wave torque, and is actually, in this case, positive. So now we have seen that the total torque depends on alpha sigma and beta t, so on the disk structure. And if you take a disk where the viscous heating balances the radiative cooling, for instance, you have its thermal structure. And in such a case, this disk will not be flared, and the temperature will decrease very steeply outward. You have a large beta T, so you have an easy outward migration. This map from Bertram Beach shows you the torque felt by a planet at the color scale as a function of the distance to the star and the planet mass. The planet mass here plays a role mainly in setting the saturation. You see that there is a large region of possible outwards migration. So many planets will migrate outward and reach here a stable equilibrium point. If they go further, they will migrate inwards back. This is a possible way that was mentioned before of gathering solid material to form cores of giant planets, possibly, but it's not so easy. There are resonances and scattering. I don't have time to develop that. Now, if you change the structure of the disk by putting stellar irradiation on top of that, the disk now gets flared. So the temperature decreases less steeply, beta T is smaller, and in that case, the outward migration is less easy. You can see that the regions of outward migration change considerably when you change the disk structure. So I refer you to the poster of Bertram Beach if you want more detail about that. And now, what about magnetic fields? Well, first of all, the MRI turbulence, if it exists, right? We have learned that it's not sure, can desaturate efficiently the co-rotation torque. It has been checked by these people here. It works perfectly well. Now, if you consider this density map, the perturbed density map of the disk with the planet here, you see that it is very turbulent due to this MRI turbulence in that case. So you expect the planet to feel a stochastic torque due to these density fluctuations. And a stochastic torque would lead to a random walk of the planet, of course. And this is actually true, but only on short term. Because if you average the density perturbation, this is what you get. So you get you come back to the older density perturbation, you recover the wave torque and possibly the corrotation torque, and so the time-averaged torque is not affected by the MRI turbulence. And now if you look more carefully at this time-averaged density perturbation, you see here a dark spot corresponding to negative density perturbation, which is due to the advection of the field lines by the elements who make a U-turn here. And this creates a new component of the corrotation torque that again promotes outwards migration. For more details on this new component of the corrotation torque, I refer you to this poster by Jérôme Guillet. I should also say that if the magnetic field is strong, actually MHD waves appear and replace the corrotation torque. This is a work by Terkem and confirmed by Froment et al. Maybe it's time to make a small conclusion on type 1 migration. We have made huge theoretical progresses since PP5, mainly due to the corrotation torque. The wave torque induces fast inwards migration. This was already known and is always confirmed. Now the new thing is that the horseshoe drag, and mostly its thermal component, enables outward migration, but it may saturate, be careful. And I think that are still open the role of turbulence and of magnetic field. There is still some work to be done here. So what we have seen, in fact, is that the amplitude and the direction of the migration depends on the disk's properties. Therefore, you should not ask us to tell you where does the planet go. We don't know. There is not a universal scenario about that. It really depends on your disk. Let's move now to giant planets. Giant planets have the ability of perturbing the disk density. Indeed, the planet exerts a torque on the disk as well as the disk exerts a torque on the planet. That's reciprocity. The planet exerts a negative torque on the inner disk, which promotes its accretion towards the star, and exerts a positive torque on the outer disk, which accelerates it and sends it away. So there is a competition between the planet that tends to repel the disk away of its orbit and the pressure and the viscosity of the gas that tends to make smooth profiles. In the end, we find the criterion for gap opening, which reads like this. This parameter P should be smaller than 1, where the first term of this parameter P is the aspect ratio divided by the planet-to-star mass ratio to the power 1/3. This compares the planet's strength and the pressure strength. And the second term is 50 alpha times the viscous alpha divided by the planet mass and the aspect ratio squared. So this compares the viscous force, the viscous effects, and the planet's force. Very in short, in clear, the higher Q is, the smaller P is, and so the easier it is to open a gap. And this is what you see here on these density profiles, shown, given to me by Willy Clay. You have various density profiles for different planet masses, from Q equal 10 to the minus 5 in black to 10 to the minus 3 in blue, corresponding to Jupiter. And there you have a nice gap open. It's a smooth process, but indeed, if you plug in this equation an aspect ratio of 5%, which is relatively standard, and an alpha for the viscosity of 4 10 to the minus 3, which is also standard, you find that the gap opens if Q is larger than 10 to the minus 3. Now, once our planet has opened its gap, it's locked into the gap, right? Here you see repulsion between the planet and the inner disk, and repulsion between the planet and the outer disk. But the disk still accretes onto the star, as shown by the orange arrow, so the planet must follow this move. This is type 2 migration, and in that case, this migration must occur at the viscous timescale, because it's just the disk going to the star and carrying the planet because it's in the gap. However, this is true only if the planet is not too massive. You can easily understand that if the planet is very massive and the disk is weak, the disk is not able to push the planet. So, in fact, as long as we are in the disk-dominated regime, the typical timescale for type 2 migration is the viscous timescale tau nu, the radius of the orbit squared divided by the viscosity. But if we are in the planet-dominated regime, this type 2 migration timescale is increased proportionally to the planet mass and inversely proportionally to the disk mass. Now, if the planet really stops the outer disk, the inner disk still accretes onto the star. So in principle, if you assume the inner disk disappears, you get a cavity like that, where there is nothing in the range between the star and the radius of the outer edge of the gap, RO. It is very different from a gap. As you can see, when I flip back and forth between these two pictures, this is a gap, this is a cavity, this is a gap, this is a cavity. In a gap, you have a void between an inner radius of the gap and an outer radius of the gap, and the ratio between these two radii is never smaller than 2. Sorry, it's always smaller than 2. Yes, always smaller than 2. And actually, in numerical simulations, there is always gas in the inner disk. It's very hard to make gas-proof gaps, and the gaps are always narrow. So gas cavities are hard to make. So be careful. The observation of a cavity is not equivalent to the presence of a planet. Actually, dust can be coupled or decoupled to the gas. And dust tends to accumulate at pressure bumps if it is decoupled. And the outer edge of a gap is a pressure bump. So it is possible to create a dust cavity with a gas gap. I refer you to this nice poster from Zhu et al., from who I borrowed this figure, where you have here the distribution of the gas surface density, the dust in size of 30 micron grains, which is well coupled to the gas. You just see a gap, no cavity here. And the millimeter dust has been evacuated from the inner disk and is not able to go through the gap following the planet. I also would like to focus on this first observation that really looks like a planetary gap to my eyes of a numericist. It has been made by Debes et al. There is indeed here a kind of gap that is pretty similar to the density distribution I got in the simulation that I did just before coming, using the parameters they infer for this system. So this may be the first real gap observed. Now, a more complicated case is the planets that have an intermediate gap so that they have an intermediate mass, so they open a shallow gap. In that case, there is a positive feedback on the drift of the planet, as illustrated by this animation. Here, what you see is a planet in blue, which is migrating down towards the star, and in red is a parcel of the gas. So the gas particle is just staying on its orbit, so we can see it go from 0 to 2 pi azimuth and back, like that. But at some point, it enters the horseshoe region of the planet because the planet is moving towards this. And there, check, it makes a U-turn, and now it orbits in the outer disk. So you see here the positive feedback. The planet is again crawling, taking material from the inner disk, throwing it to the outer disk, and then, as the planet keeps moving, this material never comes back. And under some conditions, in particular if the disk is dense enough, there can be a runaway of this positive feedback, leading to what is called type-free migration, which enables planets of the Neptune to Jupiter mass range to change their orbits inwards or outwards dramatically in just a few orbits. This is spectacular. And an application of this is that if the protosolar nebula had been too massive, Jupiter would have been lost, simply. This is a simulation I did using a really massive disk taken by Desch. And as soon as Jupiter is released, bam, it falls like a stone into the star. And then Saturn follows, and Neptune and Uranus. But if you do the same thing in the minimum mass solar nebula of Hayashi, you see that the planets migrate more slowly. Look at the time scale, 10 to the 4 years, 10 to the 5 years, and that Jupiter stays alive and is safe because it doesn't go into the type-free migration because the disk is not so massive. And here you may wonder, wait, what is happening here between Jupiter and Saturn? There seems to be something strange. What about interactions of planetary migration with two planets? You will learn that after a small commercial break. So back to migration for two planets. If we have two planets in a disk, they migrate at different rates, probably because they have different masses, and then the period ratio varies. So this period ratio, as it varies, will cross simple fractions. And if they approach slowly enough, they get captured in what is called the mean motion resonance, which corresponds to the orbital frequency of planet 2 times p plus q minus p times the orbital frequency of planet 1 is 0, where p and q are integers. To make it short, it means that the ratio of their periods, p2 over p1, is p plus q over p, so a simple fraction of small integers. On this simulation by Pierrens and Nelson, you see planet 2 migrating inwards, planet 1 migrating more slowly, and their period ratio decreases and reaches 2 here. And then it's blocked. The period ratio stays the same, but then this resonance becomes unstable for some reason, and the period ratios decrease again until they reach 1.5, which is stable. So what happens when two planets are like that in resonance? Their eccentricities grow because they are excited by the resonance forcing that the disk is making on the planet. So the eccentricities grow due to the resonance forcing, are damped by the disk, so they reach an equilibrium value. In some cases, it goes very well. Here is an example of the reproduction of the observed orbital parameters of the GJ876 system. You see in blue the convergent migration of the semi-major axis, captured in resonance, and in red the eccentricities rise as soon as the resonance takes place, and then reach an equilibrium level very close to the observed parameters, which are the horizontal lines. Now, it can also go bad. If these eccentricities reach too high values, the system can become unstable. There can be close encounters. In particular, if there are 3 planets, this is relatively likely. And then you will have scattering of these planets, which will increase dramatically the eccentricity and inclination of the planets. So this has been worked by many people. But as soon as these planets have been scattered, their eccentricity and inclination is damped by the disk. I refer you to this poster by Meng Xiangjues. And so the scattering should take place as the disk dissipates if we want to explain the high eccentricities of the exoplanets. So it is relatively unlikely fine-tuning, argues Lega et al., but it can happen. Now the migration scheme changes completely if the 2 planets open a common gap. This is type 2 migration, standard, 1 planet in a gap. But if the 2 planets approach each other and are massive enough, they open wide gaps, their gaps merge, and in the end, you have the 2 planets in resonance inside a common gap. Now, if the second planet is less massive, as you see on this scheme, the force from the outer disk will be less important than the force from the inner disk. So the object pair of planets in resonance feels a positive torque in total and is repelled outwards. Even if the disk goes inwards, the total force felt by the system pushes it outwards. This has been found by Massey and Snellgrove. And indeed, the pair will go outwards. And this can be applied to the Jupiter-Saturn case, in which we know that the mass of Saturn is much lighter than the mass of Jupiter. That could be the case of the Grand TAC model that Chin Raymond told you about yesterday. You would have Jupiter migrating in type 2 migration like that, and then Saturn may enter type 3 migration and catch Jupiter, be captured in the 3-to-2 mean-motion resonance, and then the 2 planets go outwards again. And then the disk dissipates, and this is where they stay. So this is probably why we don't have a hot Jupiter, which is quite pleasant for us. Now, what can we say about observations? Well, these are the 900 or so exoplanets that were known 2 nights ago. And you can immediately classify them in many categories. Here are the hot Jupiters. These ones look pretty normal. These ones will be the cold Jupiters, which are far away from their star. Here we have nothing, but that's just because of an observational bias, right? It's hard to find small mass planets far away from their stars. And here we get the Olympic flag. So what can migration tell us about these objects? Let's start with the hot Jupiters. I would say that 99% of the theorists agree that local formation is impossible for the hot Jupiters. The giant planets should be found beyond the ice line. Now, many of the hot Jupiters are actually on eccentric or inclined orbits, which seems not to be what you expect from type 2 migration. So it has been argued that this was the proof that the hot Jupiters were made close to their stars only due to scattering or quasi pumping and excitation. And then there would be more or less tidal damping and circularization and alignment to make the hot Jupiters on the dynamically cold orbits. So no more type 2 migration. Wait. Scattering, first of all, is generally induced by convergent migration. So you still need some migration. Also, the tidal realignment of the inclined orbits by the stellar tides implies that you should damp on prograde or retrograde orbits indifferently. So we should observe as many aligned prograde as retrograde orbits, as has been shown by Rogers and Linz, and this is not the case. If you start from an isotropic distribution, there is a problem here. Also, please keep in mind that the past mid-plane of the protoplanetary disk in which a planet is supposed to migrate could be very well misaligned with the present stellar equator. There are many reasons for that. One is that the protoplanetary disk could accrete material with a different angular momentum at different epochs of its life. A second one could be that the protoplanetary disk precesses due to a stellar companion that could just come and live if the stars form in a cluster. And this would make the delivery of hot Jupiters by type 2 migration with a spin-orbit misalignment. And in the end, I would like to remind that there are many warm giant planets on circular coplanar prograde orbits inside the ice line, and these orbits are very compatible with type 2 migration, even if the period is larger than 6 to 10 days, which is considered to be where stellar tides are not efficient at all. So for these ones, type 2 migration is a natural explanation. Then, why not type 2 migration also for the circular coplanar prograde hot Jupiters down to a period of 3 days? Now, for the eccentric exoplanets, probably planet-planet interactions are needed, that's true, but there must be a combination of these mechanisms. On the other hand, we have the cold Jupiters, these giant planets that have been seen a few dozens of astronomical units from their parent stars, like in the HR 8799 system. The local formation of these systems by gravitational instability has already been discussed this morning. It is possible, but one should be careful of the fast migration of the clumps that form by gravitational instability. And it has been already studied by many people. These clumps could migrate in very fast, then be scattered back outwards, who knows, but it must be taken into account. Another possibility would be the outward migration of a planet pair, as I explained to you, which actually, under some conditions, can go very far, as shown on this simulation. And there is also the scattering possibility for these planets, especially if they have an eccentric orbit, like it seems to be the case for the one around Fomalhaut. But remember that scattering can be helped by a convergent migration. Now we have also systems, and this is very interesting. These are the confirmed systems that we know, where the number is in the y-axis and the orbital period ratio is in the x-axis. You see a lot of accumulation close to the 2-to-1 and the 3-to-2 mid-motion resonances. We will even have coplanar multi-resonance systems, which seems really to advocate for convergent migration and then resonance locking. But there are also non-resonance systems. This shows all the Kepler candidates. And there is a lot of systems that seem to not be in resonance because their period ratio is not an easy fraction. Does it show that migration fail? I argue that no. There are many reasons, many ways of escaping from the resonance after the disk dissipates through stellar tides if you are close enough to the star, or due to planet-disk interactions. Turbulence and the stochastic forces can extract a pair of planets from the resonance. Also, the interaction between a planet and the wake of its companion, this is something new. It can repel the planets after they have been locked in resonance, and it's shown on this figure here. The orbital period ratio stops at 1.5 and then increases slowly, and this would deliver you a planet maybe here, which does not seem to be in resonance, but actually it was produced by convergent migration and planet-wake interaction. Now, concerning statistics, we have to remember that any statistic relies on the distribution of the parameters that we have input in our model. This is what people of the planet population synthesis do, and so I refer you to the next talk by Shigeru Ida, where we will probably learn a lot. There are many good things and problems in these models. I will focus here on migration. There has been interesting results by these models. First of all, if you take only the wave torque, you lose all the planets. This is what happened to them as soon as they have input the wave torque. And so this has really pushed the migration community to work a lot on type 1 migration to find a solution to this problem. Also, they need a small cavity to stop the type 2 migration of hot Jupiters. This needs also to be taken into account. And conversely, the new theories, the new models we have on migration could improve their model. The effects of the co-rotation torque have already been implemented in a few models. The planet-planet interactions during migration, I know that this is work in progress. I guess we will learn more very soon. And then the disk structure and evolution is, of course, a key. So now, what is the future of these planet-disk interactions? I think that concerning the theory of migration, we now have a good understanding of the co-rotation torque. But still, the role of the magnetic field can be understood in more detail. And the effects of turbulence as well. This will be probably the future. And we see that we rely on the disk properties. So we have to understand more the disk properties, the turbulence of the disk, what is its nature, what is its properties, and of course, the density and temperature profiles at the local scale. So I will make like everybody this week and say ALMA, 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 ALMA. It will certainly help. And concerning the relations between our models and the observations, to account for the disk structures that are observed, one needs to decouple gas and dust. There are already a few models about that. I think this is the future, and it must be taken into account to understand the observations. And for what concerns the distribution of the exoplanets, we need to understand this and improve the statistics, and this is probably the next step. But for now, I would like to leave you with 4 conclusions, easy take-home message. First of all, planets do migrate. It's a fact, if you put a planet in a gas disk, its gravity perturbs the gas disk, and in return, the gas disk perturbs the orbit of the planet. And we have strong hints from the observations to think that it happens. Concerning type 1 migration for small mass planets, we see that it can now be outwards, but the take-home message is that it depends on the disk's local properties. I insist on local. The local gradient of the surface density, the local gradient of the temperature, the adiabatic index, the viscosity is very important for type 2 migration, but also for the saturation of the co-rotation torque, and the aspect ratio. Also, please remember that a gap is different than a cavity. A cavity, there's really nothing between the star and the outer disk, the outer edge of a gap, of a hole. But for a gap, it is narrow. The radius of the inner edge of the gap is more than half the radius of the outer edge of the gap. And so not all structures that you can see in a disk are created by one planet. Either you need a lot of planets or maybe something else. I love planet-disk interactions. I would like to say, oh, there's a structure of a planet, but let's go slowly. So in the end, migration is a key ingredient of planet formation and evolution, and it can account for many observed properties, resonant or not systems. Most of the hot Jupiters probably, but maybe most likely not all of them. Also the possibility of cold Jupiters. So it is a really fundamental and, to my mind, interesting field to study. Thank you for your attention.
Thank you very much, Aurelien. So, question, let's start in the middle. Yeah.
This is to your fact on the upper left in the northwest corner of your navigational chart in the cockpit. It's a fact, it's clear that it's a fact, but the key question, I think, is how much. So from your feeling, what would be the median change, the median relative change in orbital radius, say, that you consider appropriate for planet formation in general? And what I really wanted to ask you is, how do you see the occurrence of this ultra-compact system, dynamically full systems of hot Neptunes from the, or super-Earths from the perspective of migration? So the median and the hot Neptunes.
So the median is a very hard question to address because it depends so much on the disk local properties. I think we can expect, also it depends on the mass evolution of the planet. We can expect that the planet in type 1 migration will go to an equilibrium radius, but this radius may change. If you start from an embryo, a planetary embryo, all the way to a giant planet, for instance, I think the radius may change by a factor 2 on average or so, maybe more, especially if you consider hot Jupiters that orbit close to their star while they were found beyond the ice line. But really, it's a hard question. Concerning these dynamically full systems, I think that migration can account for compactifying the systems. They would migrate, convergent migration, reach the resonances. As the gas damps the eccentricities, it stabilizes the system, and then you end up with a full compact resonance system. I think there is no contradiction, but this certainly needs more detailed studies.
Okay, Jan?
Okay, Jan Ulibert. So first to remark, the planet-plate interaction is now today on AstroPH, so it's already done. You can
Excellent,
change.
Thank you.
Then a question, you have shown that type 3 migration depends a lot on the mass of the disk. You have this nice plot where we lose everything. So I have difficulties to understand how in the ground TAC model you can have Jupiter in type 2 and Saturn in type 3. I would expect that if you lose Saturn in type 3, I mean, if you have type 3 for Saturn, you should lose Jupiter in type 3, or what's the origin?
It is a very good question. I think this is probably the weak point of the grand TAC model. A possible answer to that, in my opinion, is that we know that Jupiter went all the way to Jupiter's mass, while Saturn stopped at Saturn's mass. So Saturn must have spent more time at the mass of Saturn than Jupiter. And it could be that in these conditions that we had, Jupiter was massive enough to open a deep enough gap so that it was in slow type 2 migration. And if for some reason Saturn stopped at Saturn mass, it stayed in type 3 and caught up with Jupiter. But it clearly needs some tuning here.
Okay, on this side.
Hi, Sergei Nayakshin, University of Leicester. I want to clear up this misconception about difficulty of, a giant disk instability model, or gravitational disk instability with a rapid migration. I think people completely miss the point. The difficulty is not with this theory, but actually we are suggesting that this is how you form perhaps all the planets, because when these planets that migrate, if they lose mass, you can then explain potentially everything within one single framework. So we actually, I and Aaron Bowley invoked this rapid migration for the model to work. So only a few planets in this framework would indeed, remain at these large distances and perhaps account for those planets there. So it's not a problem of the model at all. It's actually its main feature.
Okay. Point taken. It's a good point, indeed. If they lose mass, they could be the core that we could even have giant gravitational instability, migration, loss of mass, presence of a core, and then from this core, a core accretion model at close enough to the star. Would that even work?
Unfortunately, you don't even need core accretion model in principle.
So just
it could be one framework.
Okay.
You don't know whether that works yet, of course, but that's the idea. Okay.
Okay, it is promising. Thank you. A huge evaporation rate? Why? To get rid of them? Okay. Okay. Thank you.
Okay. No question on the. I don't see on the balcony. No. Okay. So let's go back here.
Peter Wojtke, congratulations. I think the prize for the most entertaining talk should go to you.
Thank you. I hope the scientific content is also valid.
My question is about 3D models. So most of your results are based on 2D models. Now, if you have a very small planet, basically it only fields or it only interacts with a midplane. Most of the gas just goes over the head of the planet, so it doesn't interfere. Yes. So I think most of this migration one, if you have a small body, that say that the body is much way smaller than the size, the height of the disk, that should make all the type 1 migration rates much smaller. So can you maybe say a few words about 3D effects?
Sure, it's a very good question. Thank you. Maybe I should have mentioned this in the talk. Actually, in our 2D models, we have a smoothing length for the gravitational potential that corresponds more or less to putting the planet above the midplane, so that we already have some distance. And in that case, in that sense, 3D effects are roughly taken into account. Now, we have now reached computing capabilities from the computer that enable to make 3D simulations of low-mass planets embedded in disks with high enough resolution. There was already a paper by Tanaka et al. In 2002 where they compared the wave torque in 2D and in 3D, and they had a relatively good agreement, even if there was a slight difference. And now we are doing that for small mass planets, and there is a paper in preparation by Lega et al. That shows that we recover this outwards migration above 5 Earth masses in good agreement with the Pardo-Cooper et al. Things that I have shown. And for smaller masses, like 2 Earth masses, we have inwards migration again, which is in agreement with the maps I showed you by Beach. The color maps. So yes, 3D changes a little, but it does not change the global picture, and we are studying it now.
Okay, there.
Yeah, Giovanni Rosotti, MPE. So just a quick comment about the fact that it's difficult to form cavities in this disk. It is actually possible when you combine also the presence of a planet in a protoplanetary disk with photoevaporation, because by intercepting part of the mass flow from the outer disk, the planet is able to trigger photoevaporation, which can very rapidly open a cavity in the disk. So just have a poster on this if you're interested.
Okay, I will come and see it.
Raman?
Roman Rafik of Princeton. I just wanted to comment about the gap opening criterion that you showed, especially in particular an application to sort of inviscid disks, which would be typical for dead zones, for example. In this case, the criterion basically says that you need the mass ratio of the order of h over r cubed.
Yes.
And that is, about a Jupiter mass, as it follows from this equation. I just wanted to bring your attention to the fact that there is a recent body of work by many people like Duffield and McFadyen, our own group at Princeton, led by Zhao Huanzhu, and then Li, Lubo, and some other people, that shows that even low-mass planets with masses of like 10 Earth masses, 20 Earth masses, are capable of opening gaps. And in my opinion, the issue lies to a large degree in the numerical details like resolution, how you pay attention to the viscosity, numerical viscosity that arises in simulations. But I would like to hear your opinion on that as well.
I'm very, I would say, surprised. I have problems to imagine 10 Earth mass planets opening a gap.
So this is seen in simulations.
Okay, so how can...
And that holds even for simulations, including MRI.
Okay. I don't have yet a strong definitive opinion on that. I should check this work more carefully. So you said it's inviscid and then a gap opens.
Well, not only, as I said, even with MRI, you see that gaps can be opened by planets with a mass of about 0.3 of this thermal mass that you showed. So
0.3, it would open, if we follow this criterion, if you remember the figure by Kley, you would have a shallow gap. Yes, I'm not saying it's 1 or 0. The gap opening process is progressive when you increase the mass. So that you see at the beginning of a gap for 0.3, I totally agree on that. I think it is consistent. We agree when you have viscosity. The case of inviscid and like 0.1 times this mass surprises me. Thanks for pointing this out.
We can talk offline about it.
Yes, with pleasure.
Okay, yes, in the middle.
Yes, Shuichiro Inutsuka, Nagoya University. Actually, my question is very related to the previous one, but if you reduce the gas density around the planet, then you have to worry about the magnetic field because that region can be no more dead zone. So my question, could you summarize your current understanding on the effect of magnetic field on the torque, especially horseshoe torque?
Yes, I should refer you to the papers by Guillet, by Baruto, and the poster by Guillet, because they are the specialists on that. To be relatively short, what happens for the horseshoe turn is that if the gas is enough coupled to the magnetic field, when it makes a horseshoe, it carries the field lines with it, so there is the compression and the magnetic pressure outside after the U-turn. this is balanced by a decrease of the thermal pressure, thus of the density. So in the end, you have less density behind the planet. And the same thing doesn't happen ahead of the planet because the streamlines are slightly shifted towards the back of the planet. And this will create a deficit of mass behind the planet, so a positive torque.
But that is also based on the 2D calculation, right?
I think so, but the authors should confirm. But yes, I think so.
Okay, we need to make 3D modeling.
Probably.
Okay, on this side there.
Nader Hagigi for Hawaii. So you showed that planets that are close to resonance discovered by Kepler, which is correct. Now, if you put those aside and only look at the planets that have been discovered with RV, those that are in resonance, they are pretty much in resonance. So, do you care to comment on that?
I'm not sure the statistics are enough for the pairs of planets discovered in RV compared to the thousands of candidates by Kepler. We have also many systems with RV which are not in resonance, but you mean they are not close to a resonance? Was your question more on this accumulation close to the resonance, but not exactly in the resonance?
You look at planets that have been discovered with RV and they're in resonance. They're pretty much in resonance. The resonance is pretty much 2 to 1, 99.9999%.
Yes.
You know, so it is not like Kepler that are close to 2 to 1 or 3 to 2. They are right in resonance. So it looks like two different observing technique is pointing at two different things, whereas the mechanism for getting into resonance or close to resonance is the same. So that brings the question that why?
It is a very good point. I think a possibility is that, of course, I don't know all the mass ratios by heart, but this mechanism of planet-wake interaction that allows the planet to move a little bit out of the resonance and increase the period ratio, it requires a mass ratio that is favorable for this. In particular, you must have one relatively massive planet and one relatively small planet. And if I remember from the few systems I remember discovered by radial velocities in resonance, you don't have this. So possibly they were just stuck in the resonance by the disk interaction, and then they could not escape from that.
Okay, let's Amaury.
Hi, Amaury Trio from MIT. I have a question about the type 2 migration in an inclined disk. As you know, like a lot of the hot Jupiters also misaligned by more than 90 degrees, and I don't think many disks are counter-rotating to the star. But if you are in type 2, I would imagine the disk is dumped on the star, and so should deposit its angular momentum there too, realigning the star with the disk.
This would work on a small scale. I think the disk mass is just 100th or even less of the star mass. So I'm not sure it would be enough to reverse the angular momentum of the star. Concerning the more than 90 degrees issue, from Batygin paper, it is possible to go from 0 to 180 degrees, but of course with less probability to go on retrograde orbits, but still it's possible.
Okay, this will be the last question over there.
Hello, Becky Dawson at the CFA. So transit timing variations have shown that hot Jupiters are very lonely and don't even have small planets nearby, and people have explained this with planet-planet scattering, but is there an explanation with type 2 migration why hot Jupiters should end up all by themselves?
Well, there is the possibility, this possible wake-planet interaction could efficiently repel an Earth-mass planet far away from a hot Jupiter, so it would not be detected. Transit timing variations are very biased towards resonance systems, for which the TTV is much easier to detect. So I think that if you have this possibility of escaping the resonance, it could just explain this. These hot Jupiters would not be just alone on themselves. They could have more distant companions, I guess.
Okay, thank you very much, Aurelien.
Thank you.